Hello, my name is Donald O'Hare, and this is my presentation for Lab 6. So in this lab, we observed the effect of Faraday's law and Lenz's law on a falling bar magnet through a tube of aluminum foil. And so we watched to see what the induced current would do to the falling magnet, and then we timed it, and then made a glow script model of that, and then compared the two. So important concepts are Faraday's law / Lenz's law, which states that changing magnetic flux induces a voltage that opposes the change in flux. The Biot-Savart law, which relates changing current to magnetic force, and then the magnetic field of a dipole. So for our experiment, we dropped the bar through the tube 5 times, timed it each time, and that is the data. And then here's one of them. So this was the code, and this is where we modeled the the effect of the current on the falling bar magnet, and all the data wasn't exactly accurate to real life, but it was pretty close. We ended up getting 0.08 seconds instead of the average of about 1.2 in real life. So for the glow script, the clockwise current was represented by red, and then counterclockwise was blue. And we could see this, any positive current was noted to be red, which means that it would be going clockwise, looking down on it. And then, vice versa for blue. So what happens to the dynamics of the system when you flip the magnet? You would flip the clockwise and counterclockwise rotation in the of the current, but it would have the same effect on the falling magnet, since any change in flux is opposed. It doesn't matter if it's supposed to be clockwise, then it induces counterclockwise, or vice versa. It's still going to slow it down the same amount in theory. And the velocity versus time plot shows us that it was falling under gravity, and then that the induced current actually started to have an effect, slowed down, counteracted the gravitational force, not completely, but enough to slow it down noticeably until it fell out, and then obviously gravity just finished. So some sources of error are, I would say the largest one is that friction played a big part in the real life experiment, because the magnet was noticeably scraping on the sides of the tube as it was falling down. And a couple times we even had to switch to a different tube, well, before we landed on that one, since it sometimes it just got stuck. And air resistance obviously had an effect. The and in GlowScript we can't perfectly model the tube. We don't know the resistivity of it, and it's split into like 20 segments instead of one long tube, which just happens when you're bringing that into GlowScript. But I would say the biggest one is definitely the friction. So what if the resistivity of the conductor were reduced as close as possible to 0? That would make the induced current, very, very strong, since it's inversely proportional to resistance. So that would make the slowing effect really, really strong and make it fall very slowly. And what if holes or slots were cut into the tube? This would be the opposite. This would increase resistance, and that would make it fall quicker because there would be less induced current. Thank you.